Okay, so in the last video we were talking about bootstrapping, which is the idea that if you have some small sample of size n, you can use random selection with replacement to generate a whole slew of new samples as many as you can tolerate to make using your Bootstrap resampling process. So B, new bootstrapped samples, and as long as your original sample was representative, then this is great. This works in creating a much larger sample size for your task at hand. Now, what is the task at hand? Before we got to this section, we were talking about estimating a parameter. So our objective is still to estimate a parameter, whatever it may be, whether it's a mean or a proportion or a standard deviation, with a confidence interval. So at a 1 minus alpha confidence level, we are that much confident that our parameter is actually going to be in that interval that we construct. So how do we do this? How do we do this using a bootstrap sample? So every time that we have a sample, so from a sample, we extract a statistic. It may be a sample mean. So for the sake of illustration, let's suppose it's a sample mean. But if we have B new bootstrap samples, then so bootstrap sample 1, we obtain a new sample mean, which we can call x bar star 1. And then again from the second bootstrap sample, x bar star 2, and so on, until we get to the very last one, x bar star b. So we now have this new data set of just statistics. So it's a set of sample statistics, which we can think of it in its own right as being a data set. So what we do then is we take this set, sort, and find percentiles. So we will probably have our sample statistics in a histogram or the raw data set, whatever that may end up looking like. Maybe we're looking at a mean distribution of sample means. So all of our new sample means fall into this distribution somewhere. And then from here, we can arbitrarily cut off the bottom and the top alpha over 2. And then these values that determine the alpha over 2 right tail and left tail in the distribution of the sample statistics give us our confidence interval. So lower confidence interval bound here, and our upper confidence interval bound. So to recap, we take our set of sample statistics from the bootstrap samples. We then sort the data set and treat the data itself like we did in chapter 3. And we find the percentiles, right? So for instance, we have some data set from which we obtain sample means. We get the sample means. And once they're sorted, maybe they're 2.75, 3.75, 4, 4.25, 4.25, 4.25, 4.5, 5.25, 5.75, and 6.5. Okay, so let's say we have then, so how many data values do we have here? These are all sample means, right? So this is our distribution of sample means from the Bootstrap samples, okay? And we have n, our new n in this case, right? So let's call it something else. Let's call it capital N, is 10, okay? And depending on our alpha, right? Maybe suppose alpha is going to be 0.20, okay? Which makes alpha over 2 0.10. So we're looking for the 10th and the 90th percentile. And that would be cutting off the lower alpha over 2 and the upper alpha over 2 of the distribution. And from this then, using our same techniques that we did before, right? So the lower confidence interval bound is the 10th percentile of this distribution of sample means, 3.25, and the upper confidence interval bound is 5.75 plus 6.5 divided by 2. So we're taking the arithmetic means of the two values around the 90th percentile, and that will be 6.125, which means the 80th confidence interval, 80% confidence interval for mu, using all these bootstrapped samples and their sample means, is 3.25 through 6.125. And we can do this for any parameter, for a proportion, a standard deviation, a variance. We do not depend on normality, sample size, anything. The only important key characteristic here, key condition, is our sample must be obtained using the correct sampling methods.